Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems. Welcome to today's webinar, Electrical and Mechanical Characterization of Lithium Ion Battery Electrodes using Pinpoint SSRM. Joining me today as your presenter is John Paul Pineda, Park Systems Application Engineer. Paul is coming to us from the Philippines, and we had a little bit of technical difficulty with our connection earlier. Because of this, we have recorded this presentation, which I will play for you shortly. Following the video, we will still answer a few questions for you. Please enter your questions at any time during the session into the questions module on GoToWebinar. The video presentation is approximately 25 minutes. While I get the video up and running.
My name is John Paul Pineda, and I'm an application engineer here at Park Systems. And today, it is my great pleasure to give a short presentation about electrical and mechanical characterization of lithium-ion battery electrode using Pinpoint SSRM. Before we get started, I will give you a brief introduction about our company, Park Systems. Park Systems is a world-leading manufacturer of atomic force microscopes and emerging nanoscale microscopy systems. We develop solutions for many research and industrial applications, enabling advances in science for major universities, national labs, and a wide variety of national companies specialized in diverse fields. Our product line covers just about every usage case with fully manual to fully automated instrument. As you can see here, we have our research line starting from our XE7, which is a cheaper options and very economy efficient options. Also, we have our NX high vac system, which can be used in high vacuum conditions. So here, our automated industrial systems, we have our NX HDM all the way up to NX 3DM. So those are mainly used in product lines for wafer characterization purposes, and they are fully automated. And our AFM technology offers the best accuracy, the highest resolution, and is the easiest to use on the market. If you want to learn more about our company, please visit our website, parksystems.com, for more information. So without further ado, let us get started. Here is a brief outline for today's presentation. First, I will gonna give an introduction about lithium-ion battery. I will show you some sample applications. Then I will discuss how the charging and discharging process of LIB works. Also, I'm going to be showing some examples from previous study on how to improve LIB performance. Next, I will discuss the basic principle of a conventional SSRM technique. Then finally, the major part of today's presentation, I will introduce you a novel mode developed by Park Systems, the Pinpoint SSRM technique. I will explain the basic imaging principle of this technique, and I'm going to share to you the experimental results we acquired in a LIB electrode sample using this technique. So probably majority of you right now are using your laptop or smartphone in joining our webinar today. These electronic devices are actually powered by a lithium-ion battery. Lithium-ion battery are also applied in some power tools nowadays to improve productivity. In addition, it is used to power an induction motors in hybrid electric vehicles. And it is also applied in large-scale energy storage such as solar power. So compared to other battery technologies, lithium-ion battery provides higher energy density. It also have flexible and lightweight design, lower self-discharge, low cost, and longer lifespan. So if you will open a lithium-ion battery, this is the structure you will see inside. The main materials are the positive and negative electrodes, separators, electrolytes. So to achieve better performance, extensive research has focused on the development of these for cell materials. So let's further discuss these materials. The negative terminal or cathode is composed of two layers, the lithium graphite and the current collectors, which is a copper material. The positive terminal or cathode is composed of lithium metal oxide and aluminum current collectors. We use here is aluminum. The graphite layer in the anode is where the lithium ions are stored during charging, while the metal oxide layer in the cathode is where the lithium ion goes during discharging to form a stable state. And then the current collectors are the layers where the electrons flow during charging and discharging process. In between the electrodes, an electrolyte solution is used to allow the lithium ion to move from one terminal to another. These layers are also serve as a guard so that only the lithium ion will pass through the other terminal. Also, a separator is used in between the two terminal to avoid short circuit just in case the electrolyte solution dried up. So in a practical setup, all these layers are wind up together to form a lithium battery cell. So let me just give you an overview on how a conventional lithium ion battery works. So when an electrical current is supplied into a device, an electrochemical reaction is taking place in the battery. So as you may already know, electricity is created when electrons flow through a conducting material. So you might be wondering where the electrons are coming in lithium ion cell. The electrons are coming from the element lithium. So lithium is a highly reactive metal that has one electrons on its outermost shell. This element tends to always give off this electron. So when a load is applied, let's say you are using your cell phone, the electron from the lithium atom in the negative terminal separates and travel through the electrical circuit of your cell phone to provide electrical current. And then it goes down to the positive terminal to reach the metal oxide layer, while the lithium ion moves through the electrolyte going to the metal oxide and reassociate with the electrons when they meet. So the charging of the battery is just in the reverse process, wherein the positive terminal will attract and separate electron from the lithium atom of the metal oxide and pass through the power source to reach the graphite layer. The lithium ion then moves back to the graphite layer and the electron will then be reassociated. So let's move on to the lithium ion battery performance improvement. Previous studies say that understanding the electrical and mechanical properties of electrode materials plays a major role in the performance improvement of LIB. It has been shown that improved adhesion between electrode particles, electrode films, and current collectors leads to better retention of discharge capacity during cycling, especially when electrode materials exhibit faster or larger volume expansion. In addition, enhanced electronic conductivity and ionic diffusion in electrodes also lead to LIB capacity improvement. So there are methods that were introduced to measure the mechanical and electrical properties in nanoscale. Example includes nanoindentation and impedance spectroscopy. However, none of these methods can provide both data simultaneously. And then one of the more common technique used to get the electrical data is scanning spreading resistance, or also known as SSRM. However, SSRM has some disadvantages, such as rapid wearing of the tip, degradation of the image resolution, and also low signal to noise ratio. So these disadvantages are due to high frictional force arising from continuous tip to sample contact during scanning. In addition, conventional SSRM doesn't provide a mechanical data. So recently, new operational atomic force microscopy mode developed by Park Systems called Pinpoint SSRM has been coupled with SSRM to offer scientists and engineers an innovative solution to acquire both mechanical and electrical data simultaneously. In addition, uh, Pinpoint operates in an approach-retract manner, ensuring frictionless operation. So this eliminates the lateral force from continuous tip to sample contact. So at this point, you might be wondering how does Pinpoint SSRM mode work. So before we move on to the Pinpoint SSRM operation, let us first discuss the basic principle of conventional SSRM. So SSRM is based on the principle of AFM and a spreading resistance probe or SRP method used for micro and nanoscale profiling. So as you can see in the image, the main difference of SSRM and SRP is that in SRP, dual probe technique is used, while in SSRM, we only use a single probe to scan the surface. In addition, to improve the depth resolution, the samples for the conventional dual probe SRP require preparation of beveled surfaces, um, whose quality has been found to significantly affect the measured contact resistance. In contrast, SSRM offers a much higher spatial resolution and it eliminates the need for surface beveling. Also in SRP, the tip curvature radius is larger, about 10 micrometer, and the material is tungsten alloy, stylus. So while in SSRM, the tip is very small, about only 50 to 100 nanometer or even smaller, and it is a diamond-like carbon-coated tip. So here the main application of SSRM includes determination of charge carrier distribution in semiconductor and devices. So later on, I will gonna show you some examples of each applications. Right, so let's proceed with the principle of SSRM imaging. So as I mentioned a while ago, SSRM is also an AFM-based technique. Therefore, topography image can be acquired simultaneously with the electrical properties of the sample. In acquiring the topography or height image, the vertical deflection of the cantilever is measured. So as you can see here, a laser beam bounces off the back of the cantilever onto a position-sensitive photodetector, or also known as PSPD. So as the cantilever bends, the position of the laser beam on the detector shifts. So these changes are then measured and processed by the AFM controller to obtain a high image. Also, the measured changes are compensated by the AFM's feedback control, which maintains the cantilever's constant deflection by controlling the Z scanner movement. For SSRM imaging, if you are familiar with conductive AFM, the operation is almost the same. Both technique uses a conductive probe and it operates in contact mode regime. To acquire an electrical data, a DC bias is applied. DC bias current is applied between the tip and the sample. So here, the conductive tip acts as a electrode, and the direct current pass through it. Uh, Generally, this current has a very small magnitude. Therefore, logarithmic current amplifier is used to amplify the current signal before it is processed into an image. So in our setup, the resistance and conductance is calculated by the system using the Ohm's law equation, which is voltage is equals to current multiplied by the resistance. So these information are displayed in the software to map the electrical properties variation of the surface. So by knowing the resistance, one can also calculate the local resistivity by using the equation rho resistance is equals to rho over 4A, where R is the measured resistance and rho corresponds to the local resistivity underneath the probe, and A is the radius of the circular contact area. So this equation was derived by solving the Laplace equation for the electrostatic potential. Okay, so now let's proceed with pinpoint mode. So during operation, while measuring sample morphology, the XY scanner stops at each accusation. And during this pause, the Z scanner takes a rapid FD curve with finely controlled force, distance, and contact time between the tip and the sample. So in brief, an AFM probe approaches and indents the sample surface at each pixel within the area to be imaged. So for example, if the cantilever indents the surface at 256 by 256 pixels, we will expect to have about 65,000 force distance curves generated to map the sample mechanical properties. So once the cantilever deflection reaches the force threshold, the Z scanner height is recorded, and reconstruction of which will give the topography information of the sample. So here is a FD curve collected from one single data point. From this data, stiffness, modulus, and adhesion can be determined by automatic calculation process in the system. So the topography can also be acquired simultaneously by monitoring the Z scanner movement as cantilever meets force threshold. The stiffness and modulus can be calculated using a selected range of the force distance curve. And then finally, the adhesion force can be obtained after calculating the maximum from the baseline of the first distance curve. So in pinpoint mode, these properties are acquired at each pixel in the entire imaging area and displayed as image. So below are just an example of the topography and mechanical data acquired from a polystyrene and soft polybutadiene sample. So now let's proceed with Pinpoint SSRM. In Pinpoint SSRM, it is just simply a combination of Pinpoint and SSRM AFM. So this technique adopted the approach and retract operation of Pinpoint, and it collects FD curve in each contact point to calculate the mechanical data. So here, the electrical data is acquired by measuring the current flow produced by the application of a biased voltage between the conductive tip and sample in each landing point. So unlike conventional SSRM, the lateral force effect by tip to sample point contact is eliminated in this technique. In addition, this technique can provide topography, mechanical, and electrical data at the same time. So to avoid contamination and bring the best resistance data, it is recommended to conduct the test in high vacuum environment. So this will lead to sensitivity and resolution improvement. So the images here show the comparison of current and resistance image taken from high vacuum and air conditions of a silicon carbide MOSFET. So it can be observed that more features were detected in the resistance and current image taken in high vacuum compared to the one that were taken from ambient air. So let's talk about the experimental setup. The instrument that we used in the experiment was Park NX high vac. The sample we measured here was a cross-section area of a lithium battery electrode. So the sample was mounted in a cross-section metal disc holder, and silver paste was applied underneath the sample to provide an electrical connection to the bias line. A conductive diamond coated probe from nanosensors, and the model is CDT NCHR with a nominal force constant of 80 Newton per meter was used in the experiment. So here is the electrical data results we have acquired in experiment and the corresponding line profiles of each images. So the topography image shows that the sample surface consists of circular shaped plateaus with diameters ranging from 2 to 8 micrometer. So the circular plateaus with brighter colors represent areas with greater height, while the areas with darker color represents the low-lying areas. So the resistance image features brighter colored areas that represent higher surface resistivity, while areas with darker color represents areas that has a lower surface resistivity. So when comparing topography and resistance, one can easily observe that higher circular plateaus have lower resistance when compared to low-lying areas. So the darker colors on the conductance image represents areas with lower surface conductivity, while brighter colors represents higher conductivity. So in comparison of the topography and conductance images, it demonstrates that circular plateaus with higher height have higher conductance when compared to low-lying areas. So both resistance and conductance images show a clear picture of the small grains surrounding the circular plateaus. It was discovered that these small grains have lower resistivity and higher conductivity when compared to the circular plateaus. So this is the 3D overlay image of the topography and conductance, where you can also see that the circular plateaus and small grains have high conductivity. So to have a better look on the sample features, a zoom-in view was performed. So on the zoom-in image, you can clearly see the small particles which are speculated to be the conductive carbon, while the circular plateaus are speculated to be the lithium metal oxide or active materials. And the low-lying areas here are the areas with highest resistance or the high resistance resins. And then lastly, here is the mechanical data results we have acquired in the experiment. The addition image doesn't show significant variation between the plateaus, and a tendency towards higher addition is observed between the plateaus. In the stiffness images, the brighter areas represent a surface with lower stiffness, while the darker areas corresponds to the surface with higher stiffness. The stiffness image here shows noticeable stiffness variation in the sample surface. So as a conclusion, the data collected in this experiment demonstrate that Pinpoint SSRM is an effective means for measuring the quantitative and qualitative topographical electrical and mechanical data of advanced materials with improved image quality and data accuracy. All right, so that's pretty much it. So if you have any questions, just feel free to send me via here on our software. And also, if you have follow-up question, you can email me on my email address, johnpaul@parksystems.com.
All right, so that is the conclusion of the video, and Paul joins us live now. And we do have a couple of questions that came in that I will ask him to answer. And if you have any more that come up in the meantime, continue to enter them. We can always get them and follow up with you. Or as he mentioned earlier, you can email him directly or myself, and I will have my email on the screen shortly. First question is, what is the highest rate to image with Pinpoint?
Okay, so first of all, thank you everyone for listening on my presentation. So if you are referring to the scanning speed, it depends mainly in your settings. So for example, if you set a high pixel size and low scan rate, the scanning will take longer. So for the Pinpoint SSRM example, I have shown to you with pixel size about 250 by 150 pixels with a scan rate about 0.22 hertz. It only took us about less than 20 minutes to acquire the images.
All right, the next question. What are the requirements to enable Pinpoint SSRM in our system?
Well, for that, there are two things you have to consider. First, you need to have a Smart Scan software since Pinpoint only runs with Smart Scan. So just for your information, only NX series has Smart Scan and those newly released XE7 system. And then second, you need to have an SSRM package. The SSRM package is actually composed of the required module and software, as well as cantilevers to perform the SSRM measurement.
All right.
Mm-hmm.
And then I'll just wrap it up with this third one. Anything else that comes in, we will go ahead and try to reach out after the fact. What is the difference between CAFM and SSRM?
Okay. In our setup, the hardware that we use in CAFM, specifically the internal current amplifier we use in CAFM is a linear amplifier, while for SSRM, since the measured range or the range of the resistance we are measuring are wide, we are using a logarithmic amplifier. And also in the displayed data for CFM, we are more focused on displaying the current data of the surface, while for the SSRM, we can display the current, the resistance, as well as the conductance of the surface.
All right, thank you, Paul. The next webinar in this series will be held on May 27th on the subject of EC-AFM. We also have our next live demo and chat session this coming Friday at 3 p.m. Eastern Time. Visit parksystems.com/online nano academy to see all of our upcoming online content. Thank you all for joining this session. You can find more information about Park Systems AFM at parksystems.com, and please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series, feel free to reach out to me directly at richard@parksystems.com. Take care, everybody. Thank you.